Okay, so hello everyone. Today we will be solving this Leetcode problem, which is the problem of the day. I'll just quickly check if the live has started because yeah, I'm kind of new and currently I need to check if I'm currently live or not. Alright, so don't mind my recommendations. Here is this, here's my channel. Yep. And okay, I need to check if I have started streaming. Kind of new and perfect. Currently, I need to check if so let's go ahead and solve the today's problem. Currently live. All right. So this is the today's problem, and I am going to attempt this. And this is my first attempt. I haven't read the question. All right. So the question says cousins in binary tree. So this is kind of second version of this problem. However, I'm not aware of the first. So heads up if you are with me. All right. So given the root of the binary tree, okay, so it's a binary tree. Replace the value of each node in the tree with the sum of its cousins values. Okay. So first of all, what does a binary tree mean? So it means so if this is a tree node, binary tree means like it can have maximum two children. All right. And then okay, so two what else? So there is a term cousin nodes, right? So we have to replace the value of each node in the tree. So let's say this is our binary tree, and we have to replace each node in the tree with the sum of its cousin values. So first we need to crack what cousin is. All right. So two nodes of the binary tree are cousins if they have the same depth with different parents. Okay. Okay. So two nodes of the binary trees are cousins if they have the same depth with different parents. All right. So if I talk about this, so basically if you're not aware of depth, what depth of a tree is, basically if you just kind of flatten the tree, so there is a root node, and basically if you just draw the tree from the root wise, and you will see these levels. So these levels are the depths. All right. So what is the condition for two nodes to be a cousin? They should have same depth with different parents. All right. So the parents would be different. So if I call this as d equals to 1, depth equals to 2, depth equals to 3. So condition is they should be at the same depth. Let's say d equals to 3, and they should have different parents. So the parent of this node is this node, and the parent of this node is basically this node. So in this case they are different, so these two can be cousins, but these two cannot be cousins because their parent is same, right? All right, so what we have to do, we have to, okay, so for this node there could be multiple cousins, right? And same goes for this. So basically there will be a set of cousins at each level, right? In this example, basically for this node, this is these two are its cousins. So let's number them up. So quickly, this is 4, 5, 6. All right. So for node number 4, the cousins are 3, 6, right? And if I talk about wait, this was 5, right? So this is 5, 6. I call this 7. For node number 7, we have again 5, 6. For 3, we have, sorry, again, this is 5. For 5, we have 4 and 7. And for 6, we have 4 and 7. So this is, I have this quickly written down for this level. So what conditions, what we have to do for this node, for the node 4, we have to replace it with the sum of all cousin values, basically the value at node number 5, value at node number 6. So we just do this value at 5 plus value at 6, that will be replaced, right? Okay, and what we have to do at the end, we have to return the root of the modified tree, right? So basically what you have to do is to first you have to keep record of the cousins of each node, and then you have to just sum them and replace the node's value. And again, I hope this will be like kind of some copying thing, because let's say if I replace 4 with like 5 plus 6, 11. So when I coming back to 5, I won't be taking 11, I'll be taking 4 here only. So basically this should be like, we have to do operations at the original tree, right? Okay, what is written here? Note that depth of a node is the number of edges in the path from the root node to it. Alright, so that's what depth is. Basically, the number of edges in the path. So this is the root node and this is the like desired node. So what is the depth? So check how many edges are here. So 1, 2, and what this does, basically this is the same indication. So depth is like, if this is 1, this is 3, so depth is 2 only. So if you just draw a tree in this manner, it is automatically like the depth. All right, so I have to see what are the example test cases. Cool. Oh, okay, so this is kind of weird. All right, how are we saying 0 here if we have to replace it by the... Oh, okay, okay, got it. So if they have no cousin, we have to replace it by 0. Alright, so obviously for the node 5, there are no cousins here because at this level, no other node exists, correct? So, so by this time, you have to like first thing which we have to notice is that the cousins are at the same level, okay? So we have to just worry about the nodes which are kind of at the same level only, okay? So here there is this only one node, so we don't need to care. And here also 5, we have two nodes. Now we have to design our algorithm, how we will tackle this. Then we will modify this approach to handle this one, and like that we will generalize the algorithm, and then we jump into the coding. We complete this code snippet and then we test the test cases. So I know, like, I'm starting it after a very long time. I was away from algorithms, but yeah, you guys should also, if you're a beginner, you should learn how you can build a logic. All right, yeah, I might mess this up, but yeah, that is when it will happen. We'll see how to figure it out. All right, let's go with this. Okay, okay, so let's talk about this particular test case. We have 5, 4 and 9. All right, so there is this level here. What we want to do, so we have to find cousins of 4. Okay, so we have to check if 9 is cousin of 4 or not. So for that, what we can do, so we can just record who is the parent of 9 and who is the parent of 5, the basic approach. So I will just note the parent of 4 is 5, the parent of 9 is 5. So here in this case, if I go to node number 9, what I'll say, man, like, okay, so there is 9, who is the parent of 9? It's 5. And who is the parent of 4? It's 5. So here they have the same parent, which clearly violates the different parent rule. And there are no other nodes here, so for 4 my quest is ended. What I recorded was 0 cousin, right? Same goes for 9. We check in 4 and we found out like there is no cousin here, so we have this 2 zeros here. So by far what I'm doing, I'm just recording all the nodes in the level and their parents. And for each node, what I'm doing here, for each node I'm checking who can be, whose parents are different. So here we did not get any clue. Now let's go one level down. So I can see the nodes over here. Let's try it. 1, 10, and there was 7, right? Yeah. Alright, so now I'm here. I'll start forming this particular thing here. So I'll write down nodes at this level. So we have 1, we have 10, we have 7. And what I'll do next, I'll just write down their parents above them. So here the parent of 1 is 4, parent of 10 is 4, and parent of 7 is 9. So now I'm starting my quest for this node. So here I saw like only this node is worthy because it has a different parent. So we just write 9 over here. For 10, the story is same. We have this here. And for 7, we got 2 cousins. What are they? They are 1 and 10. And that's what you see. So what we do, we just do the sum. This will change to 9, this will change to 9, and this will change to 11. And that's what you see. Okay, so there is some mistake. Oh, sorry, it was not 9, my bad. This was 7, right? So yeah, the cousin of 1 is 7, the parent was 9. That is, oh, my bad, okay. So this was 7, this was 7, and this is 11. Alright, so we got here 7, 7, and 11. So by far this approach is working quite well, and I think there is no anomaly in that. So I just repeat my approach. Okay, so approach, wait, let me just bring the question back in here. I hope I can do this. Yeah. Okay, so I just need to erase it. Maybe I can just, yeah. By the way, guys, I'm using Notability, and if you're wondering which software is this, and then this is just an eraser, right? Okay, so I got my pen back, and now I'll be just writing the core logic, which might not be true, which may not be, which may be true for this case. All right, so let's go here, and here I'll do this. What is the logic? So we do this. So we have some tree over here. It's a binary tree, all right? So some nodes might have 0 children, like that. So what we'll do at each level, at every level, we list down all the nodes along with their parents, right? Node parents, pair. So we just write them all over here. And then we do one by one, we do some kind of accumulation, right? Okay, so we do some kind of, so we kind of store this in some data structure. I'll call it an array of pairs. So this is the solution which I'm discussing is purely brute force, or you can say purely what strikes first in your mind. How can you solve this problem? Then we can see if any optimization is needed, or we'll do it if I get some idea if I can optimize it any further. Right? So yeah, this is the array of pairs where I'll be storing, at each level I'll be storing these two nodes. First is the current node, and then there's the parent node. Alright, how we create this array? Obviously that's kind of an algorithm which is, in my mind I'm thinking of maybe use that BFS. Alright, so here we will be doing this now. What is the approach? For each node we just compare with all other nodes, and we calculate it, and we just replace the node's value by that. Okay, so first we need to obviously think like we just create a copy of this. So to preserve the actual values at that level, we do this, and that is quite a challenging thing. So what I went with is that if you just modify this level and then you go to this level, so this will be basically, this level will be completely changed, and it can change the fundamental meaning of nodes. Basically, earlier this was 5, 7, 8, 9, and by somehow they all became 10, 10. So if you just compare by values, you might consider these two as non-cousins, but they are cousins, right? All right. Okay. Yeah. Okay, so what I was thinking, I'll just create a copy of this, and I'll do the modifications, and I'll just save them, right? I'll just save them in some static map for each node, what will be my final outcome. And after saving it, at the end, I'll make some change which will incorporate everything. So yeah, first that approach seems fine to me. So let me repeat it for you. So what I was thinking to do, yeah, so you got me till here, that I have this, for each level I have this data structure ready, which is kind of array of pair values. And what kind of pair it stores? It stores the current node and its parent. And yeah, so I'll just create a copy of this. Maybe not the copy, just like that copy. For each node, I'll just find out who are the children's, right? And then what I'll do next is basically, okay, so I'll do next is basically I'll record. So let's say this was node number 7. So I'll record what we need to replace 7 with. So let's say I got 11. So I'll just record this, that 7 has to be replaced with 11 at the end. And I'll just store it in some data structure. Let's say it's a map of node to the final value, right? So it's kind of key value pairs. And yeah, so I'll just record it and don't make any changes. Why I'm doing this? So that these nodes are preserved in their original state when I'm currently walking through this level. Okay, so there's one more case which I forgot, was that these nodes can have same values. So it's probably not a good idea to, or I need to check if they have same values. So let me just check the problem statement over here. Okay, so what are the conditions here? Alright, so there's no condition on the value, so values can be same. Okay, so that currently worsen my problems because this approach will not work if you just do it by the values. Okay, yeah. Okay, so I just ignored a very fundamental thing which starts striking me now. So if I'm at this node, I got these two nodes over here. Yeah, so for this node, only 7 is a non-cousin. Rest all are his or her cousins, right? Same goes for this. Only these two nodes are non-cousins. Rest all are cousins. Okay, so how can we do this? So if I talk about BFS, which is an algorithm which moves like upside down, or if we just there's a very complicated approach in my mind which might mess this up. Like for you guys, it will not be simplified. Okay, so here what can we do is basically, wait, I'll just draw one more tree over here. So what's the bottleneck? Basically, when I'm at this level, I should somehow know, like, I will be able to create this list very easily, right? I should somehow know if the next node of a particular node belongs to the same parent. And how we can do that? Okay, so there is one thing in, yeah, there is one thing like comparison between two nodes, right? There's one thing over there. I'm not really sure if we can just yeah, yeah. So basically, these nodes are in itself as a data structure are unique, right? Because they point to some memory location and they in themselves they kind of point to different memory locations. So if you just treat this node and this node, they can have similar values like 5 5. They can have similar children, like let's say this is also 5, this is also 5, this is also 5. But fundamentally, if you compare it within the algorithm, they are not same. This 0, this 5 node, this 5 node are not same. So that we can easily do. So we can do this, right? So my initial approach is still rigid. What we have to do is to, okay, so we don't have to deal with values. So we have to just compare nodes, right? So if I just I create this thing over here, and there is one more simplification which just happened was this. So basically, if this node I'm talking about, so there are high chances that this node is, they are kind of non-cousins, like these two pairs, right? So I just need to check the next element if they belong to the same parent. Otherwise, rest others are kind of cousins. They all are cousins. That is for sure. Because you see, like for these two to share different parent, it's not possible, right? They'll always share this, and apart from them, no matter how large you draw this tree, how at the below levels. So basically, that is kind of all the nodes beyond this are of different parents, right? So what we can do, we just store node parent pair over here. We just need to check for this node if parent of this and parent of this are same. If it is an yes, if it is a no. So if it is yes, what you're gonna do? So if it's a yes, then you're just gonna skip this value. You just maintain a total sum of nodes in a variable, values in a variable, and what you do, you just subtract these two values from there. If it's a no, just subtract this, it it's its own value from there. Now when you come to this node, you need to check both sides, here and here, obviously, because you're not aware which side it could be. So you need to check if they have common parents. So obviously it has a common parent in this side. So when you find a parent, you just kind of subtract these two values from the sum and write it to that map. Okay, so yeah, I think I'm done with the solution, and now I'll just analyze if so what is the time complexity of it, and if it fits with the test cases which we have to consider, if it fits with the conditions over here. Okay, so there are 10 to the power 5 nodes. All right. Oh, sorry guys, I think you guys were, oops. Okay, so I'll just explain the logic again, right? All right, so let's come here. Okay. That's why we should have a live chat. Anyways, okay, so yeah, so I'll just explain the logic once again. So remember I explained this logic earlier. Yeah, so what we are going to do at each level, we are going to create a list of array which will be in a sequential manner. So let's say if we have 2, 3, 4, 5 over here, they'll appear in the same manner. And let's say the parents of these are 0, 1. So we also record the parents. So here, sorry, here we got this. Cool. Alright, so my approach is that I'll not compare the values for the parent because there is a problem with that. Let's say if these two values are same, if this is 0 and this is 0. So my algorithm, if it compares the values of parents, it will consider all of them as non-cousins. But in reality, they are actually cousins, even if it's 0. So let's keep that. Let's make it 0. That will make more sense. So what I was saying is that so in languages you can, so these two nodes may seem identical to you even if we just change these two things, but when you go internally in operating system, how languages work, when you compare these two nodes, like these two nodes, if they're equal, it will say it's not equal, which is quite obvious, right? Because this node has its own kind of life cycle. It has like it has its own kind of structure defined, and this has got its own kind of structure defined, so they cannot be same. So what I was saying, I store nodes over here in the pairs, and I compare if this node, not the values, this node and this node are actually same. There can be two conditions. One is yes, they are same, and other is no, they are not same. So what we are going to do here, we're gonna in the case of yes, what we are gonna do here, so if they are kind of cousins, for this node 2, we maintain a variable sum, which is like sum of all these nodes, like 5 4 9 12 14, right? 14 is the sum. So what, for this 2 node, what will be the answer? So we'll just exclude these non-cousins, and these two are cousins, so we'll do 14 minus 2 plus 3. And if they are not cousins, like if we just picked up, we're talking about 3 and 4, obviously their parents are not same. So in that case, for 3, what will be the answer? For 3, the answer will be 14 minus what, but 3, we have this 2 over here, so 14 minus 3 minus 2, or 3 plus 2, because obviously you need to remove 3 itself, because 3 is not a cousin to itself, right? And then 2 is a cousin. There you go. Right? And you just store these things in a separate map. Like for 2, the answer is 9. For 3, the answer is 9. Like that. And at the end, we just go to each node and we just update their values. So pretty much simple. Now let's analyze the time complexity. So we were having 10 to the power 5 nodes. So what are the operations we are doing? We will be doing a BFS to create this one, which will not take more than, like, it will be in the limit of that. It will be kind of order n only. And let's say we got this list, and what we do at each level is important, right? What will be the time complexity of it? So at each level, we're going to do this thing. So at each level, let me just yeah, so we got like this many levels here, right? And it could have, so overall the sum of all the nodes in it will be n only, and we got created with this thing, and now we are doing that operation. So it will take only one iteration to calculate the sum, and one more iteration to iterate through each node and get their final answer, because you have to just compare the neighboring nodes. Make sense? So it will be like 2 iterations roughly at each level, and it will be 2 only here only. So it will be overall kind of, let's say if it's 3, for some reason it's 3 into n. So I think it's already an efficient solution. And now what we need to do is we need to implement it. All right. So for that, I just go over here and I'll pick up this thing and I'll write the pseudocode, and then we are going to code it up. All right. So the thing is that first you need to understand, like when we, okay, so when we do this pseudocode thing, after that it becomes very easy. It becomes literally very easy to code it up, and it is kind of very much preferred approach how you solve problem in interviews. So currently we are already having a good solution which kind of passes through the complexity. Yeah, it feels at this moment. If there are anomalies, we will surely try to yeah, we'll surely try to make it work. All right, let me just grab this code snippet just for reference, nothing. Yeah. Okay, so let me switch to my note. So yeah, I remember this time, guys. I have to switch to this tool over here, and I'll just paste it. Yeah, so I just wanted this so that I can write the logic over here. All right, so what we are going to do here, so what we are given with, so we are given with the root node of the OG tree, the original tree, right? Okay, so let me this, yeah, make this good. So fair enough. Okay, so this is the OZ tree and we have been given the root node. So our approach will be to do BFS. Obviously, BFS will help you to build this. And what will you're going to do in BFS? You'll just take this node at the first queue starting point. So yeah, if you follow along with me, I think you'll learn BFS easily. So this is the next level. What we are going to do is like we just push these two nodes in the queue for next processing, and we'll push first this, then we push this, so which will ensure that in the next iteration when I'm processing this node, I'll be pushing these two first, then I'm going with this node, and then I'll push these two first. So it kind of ensures that the way I record this at each level is kind of horizontal. All right, and obviously, so what we need to have the data structures. First, let's decide the data structures. So at each level we need to create this data structure, which is obviously a array, which is vector and vector of pair of what, of nodes, right? So tree node will be passing the tree node pointers here, right? So basically this is type definition, and then we just so this will be created for each level. And yeah, that's kind of storing, that is a very simple way of storing two things at one location, which is basically the node and its parent. All right, and then there's one more data structure needed, which will be map of integer, sorry, my bad, map of node and its integer value. So this will be the final answer, and then we just do BFS, BFS, and after BFS we just do this. After BFS we just set the values, we just grab this map, and for each node we update it with the value which we are storing over here. So yeah, I think this is pretty much good, and the main challenge will be there when we get to code, but yeah, we have this picture in our mind and we'll come back to it if we face some difficulties. So guys, I'm solving this for the very first time. Like, I have never seen this problem, and I have solved only 200 problems previously, because I think I have read the concepts, but yeah, this is a fresh approach and you can also implement in a similar way, or you can just take help if you were stuck while solving, right? Okay, and obviously if you comment out the better solutions, then obviously it will make everyone to learn, right? So I'll just write comments how we are going to solve this. First we need to have the data structures, right? Data structures defined, right? So what we need here, first we need a first we need a BFS thing here, right? For BFS we need some things here, and that is nothing but a queue of tree nodes, and as we all know, it starts with the root node, and you should notice the edge cases over here. So there is sure to have one node, right? So we just start our queue by pushing the, so guys, I might have forgotten things, but I'll debug them consequently, right? So just let me just write the pseudocode, then we debug it very quickly. It won't be difficult, right? Okay, so we have pushed the queue over here. So first data structure was, okay, I'm writing this here. So we already had decided what are the data structures. So the queue was for BFS, and then we have a data structure. We have for each level, which will be, I'll be creating this in runtime, I'll be utilizing it, and this data structure will be saved, like it will be kind of at the function level. This will be at the loop level. So I'll just guide you with that. So the only data structure which we need at the function level is a map, which is basically tree node, and it's yeah, it's integer value, right? So let's name this. We call this MP or RA. So this is all kind of pseudocode, but yeah, we'll debug it later. Okay, so next what we are going to do, we are going to create for we are going to now process the levels. So here the logic of BFS comes into play, right? So while queue is not empty, let me add a note over here. If it has some nodes, we are going to run this here. And what is the first step of BFS? The first step of BFS is to empty the current level, right? Okay, and then so first we need to have an idea like how much nodes we have to process at this level. So currently, like at this state, we need to know how many nodes are there in the queue. So first we just have a variable which is L denoting the length of the queue, and it will be just queue dot size. So currently it's 1, I know, but yeah, it's kind of a globalized logic. You will learn it like as I write ahead. Okay, so now we have to like take L nodes out of the queue and push the children inside the queue and remove this node which has been processed, right? So queue is, as you all know, queue is a data structure which facilitates first in first out. So this node was added to the queue, so it's the first in. So when I process this, when I go to processing, I'll be processing this only because it was the firstly. And so queue is like this node was ahead in the queue, so when I start processing it, I'll start with this only, right? And when I add more nodes to the queue, it will be added behind this node. So that's the thing. And here I just recorded what is the size of the queue, because we are sure that whatever we have before coming to here is one level. So we need to have knowledge how many nodes are there, because we are going to push more elements to the queue which are not in that level, because obviously we are going to push the children, and children are not there, right? Children are not there in the same level, they're in the next level, right? So we need to have the size of the queue in mind, right? Now what I'll do, I'll just loop this L times, and what we will do, we take the top node over here. So do this, just do auto is kind of, you don't need to declare the type of the variable, it will automatically read it. Okay, so here we have this top node which we call it like q.front, right? So guys, this might be top, I'm clearly not aware of this, we'll debug it, right? And then what we are going to do next, so we are going to do next is basically we are going to process this top one, right? And now here comes the, so basically at this loop, at this particular loop, the bigger loop is for processing a current level. So as I told you, we need this data structure, and it's time to create it for this level. Okay, so this is data structure for storing level nodes with their parent, right? So this is the most important thing. You need to have track of parents. All right, so here we will be, okay, so we need some modifications here. Basically this queue has to be a pair of nodes, because there's no way, if I'm processing this, if I'm pushing, if I'm deleting this top node of over here, if I go to process the children in the later stage, I cannot fetch it. So what we are going to do over here is basically change this. It will be storing pair of three nodes, and for the first element, for the root we have this, the the parent of root is, wait, I'll just do like this. So I just push the root node and the parent of root is not known, so I have set it to null. Okay, so anyway, we all are aware that we don't need to set the values of the root node, right? Or if we have just only one node in the level, so we are kind of gonna skip that, right? Okay, so we need to take care of this case. So I am adding a condition here, like if there is only one node at a particular level, what we are going to do. In that case, so our data structure is probably going to be empty. I think we can handle it later in itself only. Let's focus on creating this data structure which we discussed over here. How can we efficiently create it? Okay, so we just declare a vector which will be a pair of tree node and tree node, right? And here we just define it as v. Maybe we can call it q. Sorry, maybe we can call it like level nodes, right? Cool. So what we need to do here is basically, yeah. So we just need to store it. Okay. So this is the topmost node, and what we have stored it in a variable. Now it's time to pop this out. I hope this works. I need to check the methods of queue, but that's not the issue for the moment. And now what we are going to do here is basically we are going to push this node to the vector we have here. So we are going to do this level nodes dot push back. We are going to push back. What we are going to push back here? We are going to push back top, right? And the types of these two are same. It's a pair, and here also we are storing a pair. So it is directly gonna get into it. Okay, so I'm missing a angular bracket over here. Alright, so here we just need to quickly wrap this up. Okay, I get that. Alright, so now we have to process the top node. So we have to push the children into the queue. So, okay, go ahead. So there might not be the children. There might not be the left children. There might not be the right children. So what we can do here over here is we check if this top dot first left, if it exists, then we're going to do this. And for the same thing, we are going to do for the right node, if it exists, we are going to push it into the queue, which we can do it like this. So the parent is basically this top node only, and yeah, and here we have to push the node which is basically top dot first left, right. I'll just copy the similar thing for here as well, and this will be right. Okay, the parent of both of them is this node. Yeah, sounds fair enough to me. So we will be pushing L nodes which are at this level. Makes sense. Now it's time to do the computation which we had decided. So we first need to have the first pass thing where we compute the sum. So we have sum of all the nodes that are in the current level. So how can we do that? We just have a sum variable over here. Give me a sec, guys. I just need to plug in my iPad to the charger. Yeah. So we just denoted the sum, which is currently 0, And what we are going to do here is basically going to push the values of all the nodes that are in the current level. Alright, so we're just going to go ahead and the vector which is level nodes, and here I'll just do this x dot first, and it has a value. I hope it's val. It's val. And then what we are going to do over here is basically, yeah, execute the logic over here. Perfect. Okay, so we have the sum. Now we have to go to each node and we have to subtract some like the non-cousin nodes from there, and we all know the number of non-cousin nodes can be 2 max, right? Okay, so for each node in this level node, we need to check the node before it. So here we need to kind of access the indices. So I'll just do like this integer. I'll make an iterator over here which is like this length. I hope it's size, and then we have I plus plus. So yeah, we got an iterator. So if it is the first element, if it is the last element, yeah. In these two cases, we are going to have different kind of logic. Otherwise, we have this logic. So here we are going to check for the right node, right? The next node, basically the node at index 1, if it is right. So we can do like this. If I plus 1, wait, yeah, I just do one thing over here. I just skip this. I just make it n over here, and I just have a variable which is n, and yeah. Okay, so if I plus 1 is equal to n, we are having no right nodes over here in this case. So what we are going to do in this case is basically, yeah, we have to do this. We have set the value of this node first to 0. Fair enough. And now the other way around. So now it has one neighboring node. So we need to check if, so first we need to have the parents of these two nodes. So parent 1 is basically level nodes I dot second. All right. Parent 2 is basically the parent of the next node, very next node. If parent 1 is equal to parent 2, what we're going to do here, we are going to, they are actually, they're actually cousins. What we are going to do otherwise, okay, so if they are cousins, what we have to do, we have to do this map of level nodes I dot first. Yeah, so we have to set this as sum minus, yeah, that is kind of difficult. The value is not difficult, but kind of too much code, to be honest. Dot first dot, let's do it this way, and we do this level. dot first, it will be I plus 1 dot first, and the value of it. Yeah, we are done with this. And for the basically the other guy, let me do this. For the other guy, this is true, right? This is true for them also. Yeah. So what I'm doing here is basically I'm just making this, and we need to set this to val, and for the other guy also we can set this same thing. So I just copy paste this code, and here I'll just do this. Okay, and we all know, like in the next loop, this will I will be incremented itself. But what I'm going to do over here is this. I'm going to skip the other node because we have already processed it. Makes sense? Yeah, so if they're not parents to each other, in that case, what I'm going to do is I have this val. Yeah, so in that case, we have to just care about this node only, and we just set it to sum minus val, or sorry, sum minus level nodes. I dot first val. That's enough. We don't need to increment I in this case because the next node is completely different thing. And obviously what we will be doing over here is this part only. And this part is, in my opinion, this part is independent of I equals to 0. Right? So if I do like this here, yeah. So I equals to 0 is already handled, right? And if it's not handled, for each and every node we do this. What if it is a last node? Obviously, if it's a last node, this will get executed. If it's the first node, what this will be executed. If it is not a last node, we'll just checking the next element, and we're kind of doing, yeah. Now we don't need to worry about these all cases. Fair enough. And I'll just make it I'll just fix the indentation, right? Oh, in Python you got indentation. Now look, now it's kind of fixed. So we are done with it. We have created this map, this beautiful map. And what is left? I don't think anything is left in this part. Let's check over here. So yes, everything is quite good. So I'll just quickly go through again if you are stuck with it. Now what I'm going to do is this. I'm going to do the final thing over here, which is what I have computed. I have to set it in the map. Okay, let's do it. So for that, what we are going to do, ladies and gentlemen, okay, so here we have to do one thing. We have to just compute that map. So I'll just go to the map, iterate in the map, and the first thing is the tree node. Fair enough. We have the values alongside it. So val is literally x dot second, and node is literally x dot first. And what we have to do is this node's value we have to change to val, and here we are going to return the root. Yeah, this is it. This is the entire code, and I'll just check if there are no errors. Okay, so data structures, may we have this. Fair enough. And so this is the data structure for used for like storing the values which we compute doing BFS. So this is BFS data structure. We are storing a queue which kind of tracks the parents of the queue, and the first tree node you see over here is of the current node, and the other one is for the uh, parent of that node. So for the root node we have no parent, so I have assigned it to null, and then I started with it. So we all know, like for the first level there is only one node, so that's what L will return here. L, the value of L will be 1. And there is this data structure for storing level nodes with their parents, right? This is the data structure. I'll be storing the first, for the first level we will be storing this node, right? And now we have turned this loop. So basically there's only one node over here, so it's kind of taking the front, which is currently 3, which we just pushed over here, and we remove 3 out of the picture. We store its value in the top variable, and then we remove that queue. Let's go, let's remove this 3. Now the queue is empty. Now this level is done because we have to just extract one node. So what we did was we just pushed it into the level nodes. The value we saved, this is our top node, which is no longer top because it is removed from the queue. Now we have this, so now we have this node. Now we have to push the children for the next level, and here we checked if it has the left children. Here in this case it has, yes it has, so we just pushed it. So who is the parent of that node? So this was the left node. Parent is obviously the third node which we're currently processing, right? And same goes for this as well, right? For the right side, this 2 node. And yeah, what we get at the end of this loop, we get two nodes, 1 and 2 in the queue. And now it is the time to process this level nodes. So for the 3 there is only one node, so what is gonna happen? So first we calculated the sum, which was, in this case it will be 3 only, and now we did this. So here I plus 1, I will start from 0, and here the n is basically, so this is L actually at the top. So yeah, so here this condition will hit for I equals to 0 because the size is just 3 is in level nodes here. So I plus 1 is for the first iteration, it is 0 plus 1, which is 1, that is equal to n. So this condition will be hit, and in the next step the loop will not run. So simply that's very much fine, which we wanted. And else we have this, if parents are same, we do these kind of computations, and yeah, it seems fine to me, I hope. And at the end we just set all the computed values to the real tree, right? Okay, let's run it and hope we don't get, obviously we might get, guys, I am not aware of the methods. Yeah, I am aware of the algorithms, but there might be some issues in accessing the variables, but which we can easily fix, right? That's not the point of solving a problem. Okay, so null exists only in, sorry, probably in JavaScript. So C++ might has undefined. Okay, so undeclared identifier null. What if I create a dummy node over here? Because dummy node is there. I think undefined will work. Let's see what happens. Okay, so I think because of these type definitions. Oh, let me think. What was there in C++ for undefined? It was null only, I guess. Okay, so wait, I'll just Google up. Null in C++. Okay, so it's capital null. Okay, so all caps. Yeah. I hope this is it. Okay. Finally, we are getting some wrong answers. Let's enlarge this. Yeah, by the way, guys, I'm very much happy that there was no error in the code other than that. And let's maximize the code section for a bit. Okay, so what was the problem? So we had problem at the end. Okay, can I visualize this tree? Okay, okay, so we had this, like we are printing this, but it has to be 11. So it is kind of this last level. So it has recorded it as 0 because it was the last node. Okay, so here is the error. Because it was the last node doesn't mean that 0 should be assigned. It should be basically sum minus, it should be sum minus the value of this node, which is level nodes I dot first dot val. Seems right to me. Dot first dot val. Yeah, pretty much similar to this. Alright, so this will be, in the case of 3, it's 3 minus 3. In case of... No, it's fine, I guess. It will run. Okay, so let's see what was the next test case. So yeah, this test case is basically kind of non-useful, right? I'll just try to create a test case myself so that I can test. Oh, does it happen real time? Let me check. I create two children's, two, three. Oh wow, it's real time. And then I create 5, 6. Yeah, let's check what happens for this complicated case. It works, guys. So the algorithm we wrote is kind of useful. Alright, so let's submit this up. I'm pretty much sure this is kind of order n only, which adheres to the required constraints. Alright, so let's go ahead and submit this. By the way, you should always be ready for the errors. They come. Oh, okay, guys, so this was my first problem. I have solved this problem like maybe after 2 months. I'm solving a Leetcode problem, but I'll be doing this daily, solving it randomly. Okay, so what was the time complexity? It's obviously okay, kind of obvious. It is beating 85%, so it is well acceptable, right? And yeah, let's check what is okay. So now I'll be explaining you the entire logic. So heads up, if let me check my live stream. All right. I need to see if I'm currently streaming or not. Heads up, if let me check my live stream. All right. Okay, so now I'll just explain you the logic. Streaming or not. Let me just close it. Okay, so yeah, so as I told you earlier, what was the logic behind it? Let's come to this part. Yes, here. I think you guys need this. Maybe not. Yeah. Alright, so here is the final logic, final algorithm which we figured it out. Yes, we figured it out. And here is the algorithm. So first what we did, first we thought like we need level wise traversal And we all know the best way to do that is BFS. And guys, honestly, if you don't know BFS, I'll say just go ahead and read about it. Just you need to see the first you should get the feel how BFS actually works in animation. You can find many videos which explain it in an animated way. You see the animation, you understand how they are actually processing each node, and then you just get like how then you just go ahead and write the code like we did. First we built the logic, and then we started to code, and there were errors, we fixed it, and in one go it was working. So that's how you figure it out. So don't get scared of the code you see. Your approach should be understanding how that works fundamentally. So this problem solving, this lead code thing is not about, it's really not about knowing the language syntax or something. It's about what you have in your hand, what are your limitations, and how you can get away from that problem that you have put into using them only. That's problem solving. Knowing the language nuances is good, but it is not a part of problem solving. Problem solving is just your skills, how you approach the problem, and how you just create your own logic that works very well with the conditions. Right. So we needed level wise traversal because in the problem it was mentioned that the nodes which are cousins are at the same depth level. So that itself was an indication that we need to look inside a particular level at a particular depth. So for that, BFS will help us. That was the first thing. Second thing was building the logic. So let's say how will you identify the two nodes if they're cousins or not? So for that we kind of figured it out that at a particular level there could be multiple nodes, but the nodes which are children are adjacent if we go with BFS level wise traversal, and the adjacent node, the nodes which have same parent cannot be cousin, right? That was the condition. And when that case happens only if the nodes have the same parent. Basically we have to just care about the level before it, right? That's all. So that can be, so the nodes which are kind of non-cousins are adjacent to each other, right? They could be like, for this node it could be here or it could be here. So you get this, right? Now in the problem it was asked like how we are going to basically how we're going to, yeah, calculate the sum of the cousins, right? So obviously what the basic solution, so if there was a worst solution which did not come into my mind, but yeah, the worst solution was that for each node I'll be checking if a particular node is its cousin or not. If it's not, I'll just adding up its values. So in that case what we had to do is for each node we have to do n, like for this particular level, if its size is n, we have to do n operations for each one, and it will be n square at this level. So it was, obviously it was not efficient. We might had to, if we had chosen this way, we would have to optimize it. So the already optimized way was to basically just consider the fact that they can be the parents, the children with same parent are adjacent, and you just maintain a sum variable, and rest all other are cousins. So from the sum you just remove these two or one if there are no children, if there are no particular non-cousin, all of them are cousins, right? So second thing was basically processing the current level efficiently, right? And the third thing was basically storing the results. Why this was important? Because if you changed the node values on the fly, again that will not make sense. Oh, okay, so Okay, so that doesn't make sense here, right? We don't need to store. We can actually change the nodes on the fly. No, no, we don't need. We can't change. Okay, so this makes sense here, right? So we cannot change. So basically, let's say at a particular level we have this level, these nodes at the particular level. Here, let's say for this node, this is its cousin, not non-cousin. Rest all are cousins, right? These all are cousins. So for this node, if I, so yeah, guys, we were processing mm, from left to right, right? We're processing this node, and when we move ahead, we don't, so we already have the sum, so we don't need to care about this node anymore if we are moving ahead, right? So in that case, what I'm going to propose is basically we can remove that map which we used over there, right? That will make it more better. I'll show you how we can do that. So what we're going to do, we are just going to traverse like this, and we are going to just change the values on the fly. So let's say for this we got answer is 20. We replace its value by 20 here only, right? Same for this, because we don't need to like accumulate them, because we have the sum variable. And other thing is that we are processing from left to right, so we are probably not going to need the nodes which we have processed and they are left behind. So yeah, these two were very important. This is not required with the approach which we are following, and I'll make this change right away. Okay, so these two things are required: identifying what kind of traversal is needed, and then processing the current level efficiently. It was very much simple problem, but to reach till this level, you need to really think and implement things. Okay, so let's do one change here. Now I'm saying, I hope you can see my screen. Okay, so let me just minimize this. What I'm gonna do over here is basically I'm saying we don't need this data structure which caches things, right? Which basically stores the results. We can change it on the fly because of two reasons. First is that we are moving from left to right, we are leaving nodes behind, and we have the sum calculated beforehand, right? What we can do here is basically we can just simply remove this map. Yeah, it makes sense to me. Then for this also, yeah, see, we are never gonna access I minus 1. We are always accessing I plus 1. So here what we can do over here, so we calculated this, and then we just remove this map. Okay, and we just changed it. We make an I plus plus over here, which will be making like a two-step movement. We also need to remove this. Yeah, I really hope it works. Yeah, it will work. Now we do need to do this kind of computation over here. If we just return the root one, it will be enough. Let me just check if that passes the test cases. Okay, we got compilation error. Why is that error? Let me check. Okay, so here I forgot to add this. Even here I forgot to add that. And here also. Before that we have, yes, we have done it. Now I think it's kind of enough. Yeah, let me just check if there are no errors. Yeah, let's submit it up. It is more clean. Yeah, You see, it beats 90% of the. So all of this I did on the fly, thinking how we can solve this problem. Now let's connect tomorrow. Okay, I hope you guys also solved it. And if you are stuck, you can always write down in the comment section. Yeah, that is all from my side. I have taken quite some time. Okay. Yes, I'll be stopping the recording. Bye guys, take care and keep solving problems. Here we stop the streaming.